density of whole milk. This one is 1.35. Alright, and we assume that the the reference is water. Water, basically the density is 1000 kilogram per meter cubic. So in order for you to calculate for the whole milk, okay, rho for whole milk, this one equivalent to 1.035 from this particular value. Okay, put it here, 1.35 times by 1000. So you should be able to get as 1035 kilogram per meter cubic. Okay, and then the milk is being separated to skim milk and cream with specific gravity of 1.04 and 1.01. So rho for skim milk, you can calculate. Rho for skim milk is 1.04 times by 1000. It is 1040 kilogram per meter cubic. And then rho for cream, this one is 1.01 times by 1000 equals to 1010 kilogram per meter cubic. Okay, so can you see that I am arranging and calculating all the values that can be used in order to solve the problem. Okay, whereby we have the value for the areas, we have the value for the velocity, we have the value for the rho. Okay, however, we only have the value for velocity of v1, and you need to calculate the flow velocities, of skim milk and cream. Alright, so the question asks you to calculate the flow velocities of skim milk and the cream. Alright, so how do we solve this particular problem? So from equation number 4, just now we have simplified. A1V1 rho 1 minus by rho 2 equals to A3V3 times by rho 3 minus by rho 2. So we have calculated all the values. Okay, A has been calculated. Alright, so this particular value, you need to put in all the values. Okay, I will just simplify to you. So the value for V3 is meant for the cream. This one, the answer should be as 0.23 meter per second. Okay, and then substitute this particular equation. Okay, substitute value of V3 in equation number 3, because we want to get the value for V2. So V2 equals to 1.1 meter per second. Okay, so this is how you solve the problem for this particular problem statement. And basically the total marks for this one is 10 marks. Alright, now we move on for the friction loss through pipes, because it is very common for the tubing to have friction along the line, because over sometimes there will be accumulation of deposits that stuck on the wall, inside wall of the tubing. So at certain area we need to calculate for the friction that is being lost throughout the piping system. Okay, so what you need to do is we need to calculate for the pressure drop. Okay, the first one, we need to calculate for the pressure drop. Alright, and there are steps for you to calculate for the pressure drop. So the first step is you need to calculate for the Reynolds value. Okay, for the Reynolds value. Then the second step, you need to calculate for the relative roughness. Relative roughness, this particular epsilon is being, the value is from the graph. Depending on the type of the material. Okay, so this particular epsilon, it is equivalent roughness, and the unit is in meter, and it is divided by the diameter. Again, the unit is diameter. One stands for diameter, and the unit is for meter. So relative roughness has no unit, Reynolds number has no unit. Alright, because all the units has been cancelled out. Okay, when we get this particular value for Reynolds number, we get the value for relative roughness. So you need to use the Moody diagram. Okay, you need to use the Moody graph in order for you to get the value of the friction in pipe, the F, this particular friction in pipe. So this one will be the third step for you to get for the value of friction pipe. And this particular F, this friction pipe, will need to be used for the equation of pressure drop. Okay, so how do we get the value for friction pipe? This one is by having the intercept point between the Reynolds value as well as the relative roughness of the piping. So from there, you will get the value for the F, and this particular value of F will be used to calculate for the pressure drop. Okay, the equation for pressure drop is delta P equals to 2F rho V square times by L over D, whereby L is the length, D is the diameter, rho is the density, V is the velocity, and F, this one is the friction that you have calculated. So it is important for you to get the correct value of F in order for you to get the correct value of pressure drop. If you if you find the wrong intercept point between the Reynolds and between the relative roughness, and of course, you will have a wrong value of pressure drop. Okay, and then sometimes the question will ask you what will be the energy loss due to the friction. Then this one will be fall under the fifth step, whereby you need to calculate for the energy loss due to friction. EF equals to delta P over rho. Okay, delta P is what you have calculated, the pressure drop. Okay, divide by the rho of the liquid, or it can be simplified by 2F V square L over D. Okay, this one is known as a Fanning equation. And it is important for you to calculate using the correct equation, whereby delta P equals to 2F times by rho V square L over D. Because in my previous experience, some of the students, they wrongly placed this particular L and D, or in terms of the V, it is not being squared, they are squaring for the density. So it is important for you to know and to memorize the correct equation. Okay, so this is the equation that you need to know in order for you to calculate for the pressure drop. And in order for you to calculate for the energy loss, I recommend you just to remember this particular equation, EF equals to delta P over rho. Because you have calculated for delta P from step number 4, why do you need to memorize another equation for calculation of energy loss when you can simplify by using delta P over rho? Alright, so now we move on to the problem statement. Okay, this one before that, again, these are the categories of the fluid flow in the piping. So of course, again, this one I have mentioned before. If the Reynolds number is less than 2100, then this one is categorized as a streamline flow or laminar flow. But if let's say the Reynolds value is in between 3000 and 100,000, or it is greater than 4000, then that one is turbulent flow. Okay. So now let's move on to the problem statement. Calculate the pressure drop and energy loss of guava juice drink that flow with a velocity of 2.5 meter per second through 3.5 meter of horizontal sanitary stainless steel tubing with 7.5 millimeter in a diameter. The density and viscosity of guava juice drink are 1,300 kilogram per meter cubic and 2.5 times by 10 to the power of negative 3 kilogram per meter second respectively. Use the Moody diagram to solve this particular problem. Okay, so what you need to do, the question asks you, you need to calculate pressure drop, okay, followed by energy loss, meaning you need to calculate two things. One is energy drop, pressure drop, the other one is pressure drop. The first one is pressure drop and the second one is energy loss of guava juice drink. Okay, so the velocity is 2.5 per meter second. Alright, 3.5 meter, this one indicated for the length of the stainless steel tubing. Alright, And then the diameter, this particular diameter is 7.5 millimeter. Okay, this one is diameter. And look at the unit. It is in millimeter. It is not in meter. So what you need to do is you need to convert this particular unit to become meter. Then the density and viscosity. Density is being denoted as a rho. Okay, viscosity is denoted by mu. Density and viscosity of guava juice drink is been given 1300 and 2.5 times by 10 to the power of -3. So use the Moody diagram to solve this particular problem. So what you need to do is the first step. For the first step, you need to calculate for the Reynolds number. Okay, first step. First step is calculating the value for Reynolds number. And then second step is to calculate for the relative roughness. Okay, by applying the equation of epsilon over d. This particular epsilon, you get it from the graph. Okay, can you see that this one, the material is being given as stainless steel. So you need to look for the value of epsilon for stainless steel. Okay, and then the third one, you need to get for the value of friction. Fourth is calculating for the pressure drop, delta P. For the fifth step, you need to calculate for the energy loss due to friction. Okay, so these are 5 steps that you need to calculate in order for you to solve this particular problem. And of course, it will involve the use of Moody diagram. Do not wrongly use a different diagram. Okay, so what happened here? Alright, this one I'm showing you how the problem is being solved. So the density is being given as 1300 kilogram per meter cubic. Then you have viscosity 2.5 times by 10 to the power of -3 kilogram per meter second. Velocity is 2.5, diameter is been given as 7.5 millimeter, then convert to meter, it becomes 7.5 times by 10 to the power of -3 meter. Length is 3.5. So what will be the values for pressure drop as well as the energy loss due to friction? So the first thing what you need to do is this one, first step, calculate the value for Reynolds number. So the calculation for value of Reynolds number is 9.8 times by 10 to the power of 3. And when you round off the value, it will become 1 times by 10 to the power of 4. Okay, because 9.8, this one is a very near to become 10 times by 10 to the power of 3. And then when you simplify, it will become 1 times by 10 to the power of 4. Okay, so that's why the answer is almost equivalent to 10 to the power of 4. Okay, you just round off the value. Right, and then after that, you need to calculate the second step. You need to calculate for the relative roughness. This one is epsilon over d. The epsilon 45.7 times by 10 to the power of -6. This one you get it from the graph for the steel. Okay, the value is for the steel. And diameter has been given. Diameter is over here, 7.5 times by 10 to the power of -3. So you should be able to get as 6.09 times by 10 to the power of 3. And don't use as this format. Try to simplify by using decimal point for the relative roughness, because we want to get the intercept point between the Reynolds as well as the relative roughness. Okay, so the third step, okay, this is where you are going to use the Moody diagram. Alright, so you have calculated the value for Reynolds. This one is 1 times 10 to the power of 4. Epsilon over d, this one is 0.006. So you need to get the value for the friction. So this is where you need to use the Moody diagram. So this is the Moody diagram that you have in your lecture notes. Alright. So from here, okay, this one is the epsilon. Okay, can you see that this is the equivalent roughness for a pipe? Okay, this is the value for epsilon, and you need to look for the value for the steel in order for you to calculate for the relative roughness. So this is the value for the steel is 45.7 times by 10 to the power of -6, and the unit is in meter. Alright, so this one is for you to calculate for the equation E over D, relative roughness. Alright, so epsilon over D, this one we have calculated as 0.006. So this is the value. Okay, look, the starting point is from your right hand side. This one over here, right hand side 0.006. Okay, and then, okay, so this one is the first one. First, and then followed by the value for Reynolds number is the second one. Okay, so value for Reynolds number is 10 to the power 4, is this one, this line. Okay, and 0.06 is this line. Alright, so bring together these particular two lines and find the intercept point of between 10 to the power 4 as well as for the line of 0.06. Okay, so get the line. This one is 10 to the power 4 over here. Okay, so by using your ruler, then you need to line up. Okay, so use this ruler and line up, highlight this particular line, and then after that for relative roughness, this one is 0.06, so this is the line. So the line is curvy line, so you need to follow this line, alright, and then you will get this particular intercept point. Okay, this is the intercept point of the between relative roughness. Okay, this point is the intercept point between the relative roughness as well as the Reynolds value. Okay, and then when you find this particular intercept point, so what you need to do is you need to draw the line, alright, and then get the value of this particular F. Okay, F, this one is the third step in order for you to read the diagram of Moody diagram. So can you see that this particular line, okay, this line is the intercept line for between Reynolds number and relative roughness. So this particular line, this one is located in between 0.009 and 0.01. So since the value is in between, this particular line is 0.09, the top part, this one is 0.01. So this particular value, the line for the value for this particular line is 0.0095. Okay, because it is located in between 0.009 and 0.01. Alright, so that's why the friction F, you will get the value as 0.0095. Okay, so now we have settled for step number 3. Then move on to step number 4, pressure drop. Okay, by using the equation of delta P equals to 2F rho V square L over D. Plug in the values that we have, then you should be able to get the value of pressure drop as 72.04 times by 10 to the power of 3 Pascal. Alright, and then last step is energy loss due to friction, EF. This one, just use the equation of delta P over rho. Then the answer is 55.42 and the unit is in joule. Because when we are relating with the energy, of course, it is related with joule or watt or BTU depending on the unit. Okay, so for the pressure drop, since this one related to the pressure, then the unit is in Pascal. Alright, so again, this particular problem statement will give you around 10 marks. So please get the steps correctly, and please get to know how to use the Moody diagram correctly as well. Alright, so that's the end for this particular chapter of fluid mechanics. And please do your tutorial, and we are going to discuss your tutorial in next video. And after that, we are going to continue with the next chapter. So I'll see you in next chapter. Thank you for your time and attention.